Hey everyone and welcome to PrepFusion. So today we'll be starting the lecture 16 of state space chapter, right? So we have studied a lot of concepts. Okay, I hope you are revising. Okay, in the after this lecture, right, we'll have another lecture of question sessions. So there we will solve all the questions that are related, right, between each topics. Obviously I haven't been able to take all the questions, but still as much as possible I have I've taken basically. Okay, so this will be the observability lecture, and next lecture we'll solve questions. Okay, so in this lecture what we'll do, basically, as I told, right, observability and few questions on that. So the first thing is, let us first understand, like, we know controllability, also understand what is observability. So for that, let us understand the basic concept of controllability. We already know that, but still I want to say it to you. Okay, then we'll relate that with observability, because observability came only due to controllability, right? Okay, it is not like something separate. Okay, so yeah, so first, right, what is controllability? It is basically the ability of the input to control all the state variables, right, in the system. Okay, so now let's assume that you are in a ship, right? You are in a ship, okay, and you are moving in the sea, right? Now tell me what state variables you might choose to define the state of the ship, right? So how can I choose? Basically, right, okay, let me name this as ship. Okay, now state variables of ship. So what are the state variables you might choose, right? What are the state variables you might choose? Like the state variables, right, what you might choose is basically basically, right, one is the position, basically. Okay, in where is it, like at the, let's say, in the coordinates, right, in the world map, where is it? Okay, that position. So one of the state variable will be my position. Okay, you think by your mind and then check if both of our matches. So that's why it like state space representation isn't unique, right? So you can think of any other state, and I can also think of any other state, but it should be like, it should at least define that that system, right? That should be the minimum condition. So position, let me name this variable as p, and now we have, let's say, velocity, right? Velocity is also another state, right? How fast it is moving. So velocity v, and then let's say we have angle. Okay, this, it's moving like this angle direction, this angle direction. So steering has two parts, right? Left, right, or angle it is moving. Okay, or left, right also you can say. Okay, left, right means 90 degree. Okay, if it is going straight or somewhere, it's straight only. So we can also give it angular displacement, right? Angular displacement, basically. Okay, let me name this as theta. Okay, now let me write the state equation for this. So state equation, basically, what will be the state equation? Basically, you know, right, you write it for yourself. So obviously the matrices, I don't know, right, they will be defined by the behavior of the system. So I don't know about the system, so I will just write them A, B and C. So state equation will be something like this, right? This will be P dot, this will be V dot, and this will be theta dot, right? This is A, this is P, V, this is theta, actually not Q. Okay, theta plus B, and what is, like, B is multiplied by input. Now tell me, what will you choose as the input side? Okay, I forgot to I choose the state variables, I forgot to choose the inputs. So the input side, so let me keep this here. Now think what you will choose as inputs. So what do you give, like the input in a shape, right? What do you give? So obviously I don't remember everything about the shape, because I'm not a shape engineer or something, but like one thing is, I know about the steering, right? Steering in Titanic movie, they were moving the steering. Okay, that I remember. Okay, and another one is the, basically, how much fast, right? How much fast will it accelerate or something. That thing I think they control, just similar to the car. So the input to the state variable, I will just choose these two. Okay, obviously there may be many. Okay, I will just choose these two because I don't know all the examples. Okay, so input to shape. So what are the input to the shape? So input to the shape, right, it can be the steering, right, steering wheel. Okay, steering basically. And what will be the another one will be acceleration, right, accelerator. Okay, so these two can be the input to the switch. So let me check the spelling of steering actually. Okay, the spelling was actually STEER, so yeah, I have to change it. So this is steering. Okay, so these two are my inputs, right? So that these two I will write here. Steering, let's say steering as S, and accelerator as not A. Okay, A is already there. So what can I write? I can write this one like whatever you want to write it, AC or something. Okay, can't write alpha. Let me write it as alpha, right? So steering as S and acceleration as alpha, right? So this is what I am giving the input as. So yeah, now what happens if like my this B matrix, right, B matrix becomes 0. I am giving it some input, right, steering, I'm moving, but still my ship is not moving. Why? Let's say it is stuck in some as in Titanic, like some big ice blocks came up in front, so it's stuck there, right? I'm moving even though it's not moving. Okay, so what happens then my system becomes uncontrollable, right? Then my system becomes uncontrollable because this B matrix becomes 0 even though I'm giving it some input. Okay, the input is finite, but this B matrix becomes 0. So my system becomes uncontrollable. Okay, then how will I control my system again? How will I be able to make my system come back to its normal state? Okay, so like that was the basic definition of uncontrollable, right? If this B matrix wasn't basically 0, like this B matrix has to relate all the state variables with the inputs. That was the main concept, right, in the previous lectures. So if B equals to 0, system becomes uncontrollable, right? So yeah, so basically that is the main concept. Okay, so I give you an example. Now what is the concept of observable, right? What is the concept of observable? So let's assume you are observing, right? You are the driver. Okay, you are observing that there is some that the ship is not moving due to the input. Okay, and you're observing the output. Okay, and if you now observe the output and take the output and give it to the control element somewhat, so that it can move, right, in some other direction. Okay, let's say this B matrix isn't completely 0. Okay, it is somewhat 0, like few states are controllable and few aren't, right? Now the states which aren't controllable, instead of we can't measure them, right? Because if the state aren't controllable, then as I told you in the previous lectures, that we aren't able to measure them. So what I will do is I will observe them. I will observe the state of those. Okay, let's say I can't measure the position of the ship, so I will observe my eyes will observe the position of the ship basically. Now I will send that data. I will take the data and I will send the data to the input, right? And with the help of that I will be able to make my system controllable again. Okay, so that is a basic concept. Even if my system isn't wholly controllable, what I can do is I can observe the individual states, right? Okay, which aren't controllable, and I can sense them. Okay, not sense them, I can observe them and take that data and give the data to the with the input with the help of a state feedback that we did basically, and I will be able to control all the state variables. So basically what is the crux is, previously if a system was uncontrollable, I wasn't able to measure all the state variables, right? Okay, I wasn't able to measure all the state variables, and I have to measure all the state variables for me to give it to the feedback and get a control input, so that I can control my state, right, system. So I can control my state of the system. But now what I'll do, even though few state variables are not controllable, okay, they are not related with the input, even though I can't measure them, what I'll do, I will observe them, okay. Then obviously I will write all those things, then you will understand it a bit better. I'll just explain it to you. I will observe them, right. After observing them, what I will do, I will take that data, and now I will have the data of all the state variables, right. Now I can measure all the state variables. So yeah, then I will give some control input, and then I will be able to control my state of the system, okay. So yeah, that is the main thing. So like I will not write it here, okay. Let's just write a bit, okay. Let's say my eyes whatever I see in my eyes is the output, okay. Like my eyes observe the position, velocity and angular displacement. Okay, angular displacement. Okay. So this is basically what my eyes did. So what I can do is, now my eyes are capturing this data, right, observing this data. Now I can give this captured data to feedback to the state feedback. For getting controlled, for controlling the state of the system. Now how we do all this, obviously I will write it down, and then we will understand a bit better. The feedback for controlling the state. Okay, state of the system. So yeah, this is basically what we do, okay. Now right now, like what happens if I close my eyes? If I close my eyes, I'm not able to observe anything, right. I'm not able to observe anything. So if I close my eyes, I won't be able to know the position of the shape, the acceleration of the shape, and the angular displacement of the shape, right. So then I won't be able to observe the states, okay. So that is what basically observability means. So observability, right, observability, okay, this is wrong. Observability means to observe states, basically observe states, okay. And what does controllability meant? Controllability meant to control the states, right. Control. Now why do we want to control the states? To stabilize the system, right. Make the system stabilize, or we want to get our desired state, right. That also is true. Stabilize the system. And why do you want to observe the states? To detect the states, right. To detect the states and give it back to the state feedback to basically control, okay. That is basically the concept of observability. So concept of observability only comes due to controllability, right. To detect states, right. So yeah, these are the two things, okay. So now right, so this is what the basic understanding of observability is, okay. Now we will go to the few key points for observability, right. Key points for wait. Observe way. Oh no, something is wrong. This is bad. Observability. Okay. Observability. So I think there is only single L. Sorry. Yeah. So yeah, what are the key points for observability? Basically, right, system is said to be observable or output observable. Like, don't confuse this with output controllable. That was different, okay? And that doesn't also come in exam, but we have to know all those things just in case if it comes, right? So system is said to be observable or output observable if it is possible to observe all the state variables by measuring the output within finite time interval. What does it mean? So basically, right, it is telling us that we are able to observe all the state variables. That is what this is basically telling, right? So then the system will be called observable, right? We are able to measure all the state variables from the output. Okay, from the output we are able to measure all the state variables. From the input I was not able to. Okay, from the output I can measure or I can observe, right? Then also, like, observability defines that the output depends on all the state variables. Like, basically the same thing. Basically, that is, if there is some change in any state variable, then that change will directly reflect at the output. So yeah, the relation, there should be some direct relation between the output and the state variables. So if there is some change in the state variables, that should reflect in the output. So that is also what observability means. Now observability is the ability of the state variables to affect the output of the system. So in saying the same thing, right? State variables can affect the output of the system. Okay, now this is another key point. Observable systems are those systems from which all the states are observable from the output. So, like, again the same thing, right? We are like calling the same thing, like observable systems will be those systems where I can observe all the states from the output. Yeah, same. Even if the system isn't controllable, then we can make the system controllable with the help of observability. Yeah, this is also another important point. Even though, like, the system isn't controllable, that is fine, okay, but we can make it controllable with the help of observability. We can like observe the state variables and feed it back to the state feedback. Okay, that is what we can do. But you might ask, like, how, why don't you measure it directly? Why can't you measure it directly? Why, how am I able to observe but can't measure? Okay, all these things we'll slowly study and then we'll understand. Okay, so like, what did you learn in previous lectures? The state feedback, right? The state feedback. So the state feedback, basically we know this one, right? For the state feedback, there is some reference signal and we measure all the state variables. Okay, measure the state variables. State variables, okay, and then we feed it back to the feedback, and then we get a controlled input, right? Okay, that we give it to the state feedback. Okay, so that is what we do. Okay, now let me write the equation once more. We know already this, but still let me write it. So this is u r minus kx, right? U r minus kx. So what is x dot? X dot is basically, right, so this was a times x plus u times b. Now my b, like, b is b only, but u changes to r minus kx, right? So my x dot, right, is basically a minus bk times x plus br. Okay, plus br. So yeah, this is basically what my x dot is, and my y was cx, right? Y was cx. So this one, right? So one thing to notice here is this a minus bk. So if I can't measure all the state variables with the help of this k, right, like the K is a matrix, right? And if few columns are like rows are 0 or something, I am not able to control that particular state variable, right? I'm not able to control that particular state variable. Okay, if my rows are like few of the rows are 0 for this K matrix. Okay, I hope you understand. So like then if all the states are not available to measure for state feedback, then my system won't be controllable, right? Few of the matrices will be 0, then system is uncontrollable. Okay, so then my system is uncontrollable. Okay, so we won't be able to control the system. So in reality also, in actuality, like what control engineers used to do is they don't measure all the state variables, because some may be inside the chip or some may be aren't able to measure, or some are very costly to measure, right? Sensors are very costly. Okay, so we don't want to use that much money on all those things. So what we do, we measure few of the variables and we use the concept of observability. Then with the help of that we control our input. Okay, so with the help of observer, we can control our not input, our state. Our state, right? So yeah, now what is the observer? So observer is this one. Okay, like the observer that we use is Kalman's filter. Okay, so like this is just a block diagram representation. In the next few pages we'll totally go in depth of this block. Okay, so what is a Kalman's filter? Basically it has two inputs and one output. Okay, two inputs and one output. The output is the estimated state. Okay, we'll estimate the state. Obviously we're observing it. We'll estimate the state with the help of our input and this y. Okay, with the output. Okay, with the help of the output and the input. Okay, both of these things. So this is the, what is this? Let me use different color. This one is good. This is the output due to all the measured states basically. And what is this? This is basically normal input, right? This is normal input. Okay, normal input to the system, input to the system. And what is the other thing? So this, right, this is the estimated state variable or detected state variable. So I can call this as detected. Okay, this is known as the detected state variable. So what is my x cap? So my x cap, right, is known as the detected state variable, right? Detected state variable, or we can call this as observed state variable. Okay, variable, let me, okay, state variable, let me keep it at the last. We can call this as detected observe and estimated state variable, right? All of these things we can call. Okay, all of these things we can call. So basically, right, like now, how does the observer, you might ask, how does the observer estimate this state, right? How does the observer estimate all the states, okay, without even measuring? Okay, so we'll prove this one. Okay, we'll prove this one. But first thing we need to know about the Kalman's filter is, Kalman's filter is also a dynamic system, and it is related like the our original system itself. Okay, so Kalman's filter is also a dynamic system, and it is related like this one. So my measured, right, measured state variable x cap dot x cap dot is equals to a x cap b, and now I have two inputs, right, y, and my output is also y cap into c x cap. Now you might say, like, sir, you have like written the same matrix, are those same? ABC are same? Yes, ABC of the actual system and this Kalman's filter will have to be same, right, for the proof to happen and for us to measure the state variable. So Kalman's actual system will be same. Okay, so these two things will be same, right? So one more thing I can write, like I will take one feedback from my this approximated value, right? Okay, what type of feedback to make it more faster? Okay, to like change, I will change this y, so I can write my y like this one, right? So what I will do, my x hat, right, x hat dot will become something like this. It will be ax hat only. Okay, then this will be by, okay, plus some y minus y hat, okay, and kf. Okay, so yeah, we will understand this, why this y minus y hat comes and all this. So this is just to make my system faster. Okay, make my system even more faster, make my system faster to reach steady state. Okay, always we use this feedback for us to reach the steady state in much more faster manner. Okay, so yeah, obviously this all this also will study in time response, there also will understand. So yeah, this is one thing that we needed to understand, right? So basically, right, basically now we will use the block diagram and explain to you the pictorial representation of observer and how we control the input even though the system is uncontrollable. Sorry, not input, control the state even though the system is uncontrollable. So yeah, this is the block diagram of system with observer, right? This is the block diagram of system with observer. So right, we have, let's say we have one state variable here x, and this is x dot, like state variable matrix. Okay, multiple state variables we have. So this, right, this is the normal block diagram that we know without the observer. Okay, normal block diagram of the system without observer. So this figure, right, okay. So this is without the observer. And what is this? This is basically the observer, basically observable. So I should write this here, system without observer. So let me copy this here first. This is the observer itself. I will explain everything. Okay, observer, and this is system without observer, right? Okay, this system without observer. So now, right, now basically this block diagram we already know. I'm not explaining it. This one, what is this one doing? So this is the output, okay, from this state, as we can't measure all the states. So here, right, we are not able to measure all the states. Not, let me write this in small actually. Not able to measure all the states. Okay, so we are not able to measure all the states. So yeah, this is basically the thing. So here what we will do, we'll take this like output, the whatever state variables we can measure, and according to that output we'll give this input here, and this is the estimated output. Okay, and also we'll give one feedback, and then we'll subtract these two, and this right, this will go to the state feedback. But as there is no like this feedback here, this will behave as a slow network, right? Now the modification that we make, we don't take the output directly from here, we take the output from here, the error, right, between y of s and y, estimated y of s, and we give it to the feedback. Okay, give it to the feedback, and then the system response is much faster. Okay, so like with feedback, this is the figure. Okay, response much faster, right? System response is much faster. Okay, system response is much faster. So this is basically what you do in observer. Okay, so what is this doing now? How are you getting like this? How can I measure all the state variables here? That I will explain it to you. Okay, so this, right, I will be able to measure all the state variables here. So with the help of this one and this one, like at this point, all the, like I will prove it to you how I'm measuring. I'm just stating right now. We'll do the proof, right? All the state variables. Okay, all the state variables are measured, right? Let me, so yeah, so this is basically it now, right? Now I will connect all of these things. So this was my actual system, right? Initially, I hope you understand, this was my actual system. Okay, then I will explain one by one. Now this was my observer here, right here, and the output, right, like the input to this one, there were two inputs, this one and this u of s. Okay, there were two inputs, right, this one and this u of s. So yeah, this is my another input, and this is my another like reference input, right? So Okay, I think this u of s should be connected like this one. Like u of s is same only, right? This u of s and this u of s are both of them are same, so I can connect them here. Okay, so basically, right, this is my observer. Okay, at this node, node I can measure all the state variables. Hence there is a state feedback. I can give the state feedback now. State feedback as all the state variables now, as I'm able to all the state variables with the help of observer, right? Okay, so yeah, this is the thing that we are doing, right? And now you might ask that how am I able to measure all the state variables? This we know, right? This is the state feedback that we know basically. Previously we were taking it from here, okay, but as we aren't able to measure all the state variables, we do some theorem and something, okay, and then, right, I take the feedback from here, and the same thing that we used to do, control the states, right? Control the states. Now what we will do, we'll do the proof, right? So proof. Now let's prove that our estimated state will be almost equal to the actual state. So estimated state will be almost equal to actual state. Estimated state will be almost equal to actual state. So now, so how to prove that? So we have to make the error 0, right? We have to make the error 0, that the difference. So for this, the error, right, what is the error? Error equals to x minus x hat, right? This is my error, and we have to make this 0 so that this becomes equals to this one. Okay, so where is my x hat and where is my x? So I forgot to write here. So this, right, yeah, this one is my x hat, and this one is my x hat dot, and this one is my normal x, and this one is my x dot. Okay, so yeah, these are the two things. So I have to make these two, like this error between them as 0, right? Okay, like this actual state, okay, this the measure I can take because due to this u, okay, but actual state of the system and this x hat should be 0. Okay, that's how we will understand that even though without measuring I'm able to I'm able to estimate my actual state, right, without measuring the states. Okay, so yeah, let's write the normal equations of state equations. So what are the normal state equations? So state equations, right, one is x dot, okay, then we have a times x plus b times u. This is one equation, right? Okay, this is the normal, this equation, here, right, this equation, here u is coming, and here like x into a is coming. Okay, this is a normal equation. Now I will write this equation, right? I will write this equation. So how will I write this equation? So, right, first of all, like let me write this x hat of dot, what is incoming here? So again, this x hat is incoming, okay, this b into u is incoming, okay, and one more thing, this one is also incoming, right? The state like not the state feedback, normal Kalman feedback, right? So what is this? This is y minus y hat of s into k of f. That's why I had two inputs, right? This one and this one. Obviously state is there itself, so in the block diagram at the starting, right? So this is ax plus b b times this u, okay, then also I have this one, right, this one. So this one will be plus kf into y minus y hat, okay. So this is my equation, okay. Now what is y minus y hat? So y minus y hat, right? So it is ax plus bu plus kf into, what is y equals to? We know, right? Y equals to, so let me write here. So y equals to c times x, this already we know. And here, right, here also y equals to y hat equals to c times x hat, right? So this is x hat, and y hat equals to this c block, gain block times x hat. So that this we know. So we'll replace these two here, okay. Okay, and so what I will do, I will like basically get x minus x hat, right? So this is my x hat actually, okay, x hat or dot basically. So now I will change this, okay. What I will do is this is my, what is this equation? This is my equation 1, and this is my, let's name this as the equation 2. I will subtract equation 1 and equation 2, okay. So subtracting 1 and 2, right? So if I subtract 1 and 2, what do I get? So this becomes like x dot minus x hat dot equals to simply a x minus x hat, and this bu cancels, right? Bu cancels out, okay. We are only left with this one, okay. So this one comes as minus times c is also in common, into x minus x hat into kf is just a matrix, okay. Kf, I think one thing I did draw, kf should come at later, right? Kf is here, okay. After this kf is getting multiplied, so this is a matrix, so we have to be very careful. So kf will be not at the start, kf will be at the back, okay. C will be at the start, because c is getting multiplied early and kf is getting multiplied late. So matrix multiplication, don't mess up the orders, okay. So yeah, kf is at the end, okay. What did I do now? Okay, so yeah, this is basically after subtraction that I get, right? So now how can I write this? So this is something like differentiation of time, right? Both of them are differentiation of time. So what I can write here is ddt of x dot minus x cap dot equals to a x minus x cap minus c x minus x cap into kf, okay. This is my x minus x cap. Now what is my x minus x cap? So x minus x cap, right? So so I can, what I can do, I can take x minus x cap common here between all these two, right? So that is what I can do. So what I will do, like this x minus x cap is just a function of time, so I can take that common. So this becomes a minus c kf into x minus x cap, okay. And this is ddt of x dot minus x cap, okay. So now, right, now what is this x minus x x cap equals to? Sorry, this is not dot anymore, this is normal x minus x cap. So we've already written it here, it is error, right? Error, the actual estimated state and the actual state, right? So whatever will be, if it is non-zero, then there is some error. If it is zero, then there isn't any error. So hence, if this is like 0, then what do I get? I get this as delta of t into t equals to this a minus c kf matrix, right, into error itself, okay. So now, like this is just a first order differential equation. So we'll have, this is a matrix, so we'll have like eigenvectors and eigenvalues of this, and those should be negative, okay. Those should be negative for my this error to decay down, right? For this error to decay down. Now you might say I'm not understanding anything. That's fine. So what I will do is assume it's a single order system. So assume single order system. So if it is a single order system, right, my the elements, right, will be only a single element, okay, a minus cf. So I can simply, like, instead of matrix element, I can simply solve this differential equation which we have solved in class 10. I think, I don't remember. Okay, ckf, and this is just a single element, right? A minus ckf is just a single element. So if I solve this, right, differential equation, what do I get? This is basically de by e, and this is, let's say this is 0 to e lambda. Error is going from 0 to lambda, and like this is going from, like, no, not 0, sorry, this is in, like, not time bound, right? And this is, let's say, a minus kf into dt. Okay, so all this is like indefinite. Okay, so this is ln of log, ln of error, and this is simply t times a minus kcf, right? ckf. Okay, so what do I get? So this, right, like, what is in a single element, like a minus ckf, known as, like, what is a known as in a single element is known as the lambda, right? We know it is the eigenvalue. So like this, we have already learned this. If you don't remember, you have to again revise. This is known as the eigenvalue. Okay, so I can replace this whole thing with lambda, right? I can replace this whole thing with lambda. So this will be lambda t. Okay, so what I can write here is my ln of e equals to lambda t. So I can do exponential inverse log on both sides. So my error, right, error becomes a function of lambda t, and it becomes a function of the eigenvalue, right? Now, right, eigenvalue has to be negative, obviously. It can't be positive. So first point is the eigenvalue should be negative. What is the second point? It should be very high in the negative direction. Okay, so that my error reduces much faster. That's why this feedback is there, right? It is pushing it to the negative value more faster. Okay, this negative feedback. So if my kf is, let's say, if only I had a, right, so a was -1. Okay, a was -1. Now it would have become e raised to power minus t. Okay, now if my, like, there is some feedback also, and let's say kf is 2 and c is just say 2, it becomes 4. -1 minus 4, it becomes -5. This is e raised to power minus 5t. So my error, right, with time, it is much faster towards going towards 0. So that's why feedback makes my system much faster. Okay, so I hope you got that practical approach here. Okay, so yeah, that was one thing about the error. Okay, so what do you understand? Feedback helps making more negative. Okay, so that to make, I should write, the first point is to make error a decaying function. These 2 points should be corrected. So this, hence like hence the eigenvalue should be negative simply. So yeah, so I'm not writing it anymore. So eigenvalue should be negative. Here I have already written it. Okay, so yeah, have you understood, like, why you used feedback, and obviously how you observe the system, and the error is coming out to be 0. Okay, just for one cross one element, because this proof, right, no one tells you even the proof. I gave you the intuition and all those things. People directly go to this topic. Okay, now what I will teach you. Okay, even this proof they don't give you. They directly go into the conclusion of the proof, and that is fine. Okay, you can you don't need to remember all this. You just watch through these proofs very fast. Okay, very fast, and just to get a basic idea and intuition behind what is happening, right? So this is my, like, what is Kalman's test for controllability? It is similar to the not controllability, sorry, observability. It will be actually observability. It will be similar to the controllability part, right? Observability. Okay. Yeah. So yeah, what we will do again, we write the state equations, right? So what are my state equations? My state equations are x dot of t equals to a x of t plus b u of t, right? Now what is my y of t? Y of t is this one, and it is c x of t, right? So basically what I want to say here is, like, what I will assume in this case is my input is 0. Okay, I will assume my input is 0 for easier calculation. So I will get find the 0 input response. Okay, so input to be 0. Okay, if my input is 0, so like what will be this x dot of t equals to a x of t, right? If x dot of t equals to a x of t, then I find the 0 input response, and my y of t becomes c x of t, right? Y of t becomes c x of t. There is no input, right? Anyways, D matrix was 0. So my x of t, what does it become? It becomes e raised to power at times x of 0, right? Okay, x of 0. I hope you remember all this thing. So this is the state transition matrix. Okay, and this is what I am writing. This is the 0 input response from the previous classes. I hope remember, right? Now I will go very fast, right? Because I've studied this, like I've taught you all this in details. Okay, so now what will my y of t become? My y of t, right, it will become c times x of t. X of t is e raised to power at times x of 0. Okay, this will be my y of t become. Now what does as I told you, right, what does an observable system means? Observable system means I can observe all the input states. Okay, all the input states with help from the output, right? I can observe, like all the states can can come to the output, right? There should be some link between the output and the observed states, as I have given the definitions. Okay, now let's prove it, right? So basically what I can break this down, e raised over at as a function of alpha, which is a function of time, and then matrices, right, with respect to a. So what I will write here is this y of t will be c. Okay, then let's say this is alpha naught t times I plus alpha 1 t a. Okay, and this is alpha 2 t and we are going up till n minus 1. Okay, then t, and this is a raised to power n minus 1, right? And at the end, what do we have? Let me reduce the size a bit. At the end we have x of 0. Okay, at the end we have x of 0. Now what does this further become? What I can do is multiply this c inside, right? Multiply this c inside. So like this alpha naught t is here itself times c. Now this is alpha 1 t can go outside. It is just a time value, so it goes on the left hand side. I have c times a, and this will keep on continuing, right? C, like alpha 2 t into c times a square, and this will keep on continuing up until the last element n minus 1, which is c into a raised to power n minus 1. Okay, and this is x of 0. Okay, so yeah, now what is my y of t equals to? What is my y of t equals to? So my y of t, right, what I can do is write this in terms of another matrix that will be same form as this one, as this is telling, right? So what I can do, I can write this matrix as alpha naught of t, and I have alpha 1 of t, and I have x of 0 also, and I have this what do you say, alpha 2 of t, then this is going on until n minus 1 into t, and what I can do is simply put this x of 0 here, right, and write the C matrix at the end. Now don't worry if you don't understand the proof, because this proof is nowhere near important, okay. Only solving the questions is important. So yeah, this proof won't come anywhere, just to give you the basic feeling, okay. I get like a column matrix this time. Previously what I was getting like a row matrix, right. So this is C A square, and this is keep on going until C e raised to power n minus 1, okay. This keeps on going until that. So if you don't understand like how I did it, no need to, okay, no to worry. So just one thing you have to understand is the main thing that the conclusion that I will come to is, like, now I have again the Cramer's rule, right. What does the Cramer's rule say? So again I have this equation at a1x1 plus b1y plus c1 equals to d1, okay. Now what is other? a2x plus b2y plus c2 equals to d2, right. And a3x plus b3y plus c3 equals to d3, okay. So this is the Cramer's rule basically. So like for observability, what are my xyz? So xyz is basically this one, right. This one is my xyz, okay. So it was like xyz here and this abcd matrix. Now what I will do, I will multiply this inverse over here this side and this matrix, right. If I have to multiply inverse of this one, then I will get a certain solution, right. d1 d2 d3, okay, certain solution. So for a unique solution, okay, for a unique solution, this rank of this matrix should be equals to the order, right. Rank should not be less than n, okay. So like okay, let me explain it to you. So this is what I will do. I will again copy this. I will multiply the inverse, okay, on both sides. Now for me to get a proper solution, right, this is my xyz, this is my function that I try to get my unique value, right. So what I do, I can replace this in matrix format, okay. Then you will understand this is a1 b1 c1 a2 b2 c2, and this is a3 b3 and c3, and this is my x y z, okay, d1 d2 d3. Now you remember, right, this delta has to be non-zero. This has to be non-zero, okay, for me for getting the unique solution. So delta has to not be equals to 0 for unique solution, okay. So basically this delta needs to be not to be 0 basically, right. The rank of this one, if delta is not equal to 0, then obviously it will be full rank matrix, basically the whatever the order is. So hence for getting unique output, right, why do I want a unique output? So that all the state variables I can find, right, all the state variables is observable to me, okay. Else if the rank is not 0, then my output will be 0 for a particular state variable, right. I won't be able to observe that state variable, okay. My output will be 0 for that particular state variable, okay. Hence the rank should be non-zero for me to observe all the state variables, okay. If the rank is less than n, okay, this is n cross n, okay. I will understand like how this is n cross n, like this is just a column matrix, however it link, this is n cross n, right. That I will explain it to you. So like yeah, for my system to observable, for my system to take all the state variables, right, to see all the state variables, okay, get the values of all the state variables, this has to be a full rank matrix. Full rank means the determinant should be non-zero. Full rank means whatever the order of the matrix is, the rank should be same as that. So this matrix, right? This is known as the observability matrix, but in a different format it's known. So I will not write the observability matrix. I'll just write here that this, I will copy this one. Okay, this is already copied, I think. Yeah, this matrix should be full rank. Okay, that is basically rank of, like as I have already explained the controllability proof, right? So I'm skipping a bit of part because this is anyways not that important. Just want to get to the conclusion of how the Kalman's rule came, just to keep in your head so that you can even remember it in a better manner, right? So just to, for that reason I'm explaining the proof. Proof is not that important. So this is CA and this one CA n minus 1. Okay, rank of this one should be n, right? Okay, this is n cross n. This is n cross n, right? Yeah, sorry for the interruption. Actually my storage got finished, so I had to again restart. So where was I? Like, how is the order n cross n here, right? So what is the C matrix? C matrix, if you know, right? C matrix, what is the order of C matrix? It is p times n, right? It is p times n. So now if I assume it has one output, so it is 1 times n, so it is a single row only, right? And assume it is 1 cross 3, so I will have 3 elements. Okay, so the first row, right, will have 3 elements in it. Okay, then what will be the second row? Second row again, right? C times A, what will be the order of C times A? So C has 1 cross 3 and A has 3 cross 3. So this 3 gets cancelled and we are remained with 1 cross 3. So again for the second row we have only 3 elements. So this will go on until 3 rows, right? So I'll have a 3 cross 3 matrix. So in the first case, in controllability case also we did something like that, and here also we're understanding. So even though it is looking like a column matrix, but this is actually a square matrix because C itself is a matrix. Okay, try to keep that in head. Okay, so but now in books you might ask, you might say that sir, like in books I see some different format of this observability matrix. You are correct. Okay, you are correct only because what happens is that this matrix, right, is not written like this. In transpose format it is written because of one basic reason is that this takes up too much space, right? Too much of lines. Okay, we want to write it in a single line. That's why we take the transpose of it and then solve. Okay, so that is the simple reason of why we do this. Okay, so yeah, then basically, right, so let me write the observability matrix. I will take the transpose of this one and then you will understand. Okay, just to write this in single line we take the transpose, and you might ask, then the answer might say change, right? So you said, right sir, like this one should have like a rank of n, and if I take the transpose of it, then the rank, the condition should change. No, the rank of a matrix, okay, or rank of a square matrix basically, if it is some value, then even if I take the transpose of that, it will still remain the same. I will prove it to you. So yeah, I will write the observability matrix later. So let me first prove this thing. So I will take the transpose of this one. So what is the transpose of this one? Transpose of this one, right? The transpose of this one will be, look, what is say me, this is one property I've already we know this. So what is the transpose of A B? It is simply B transpose A transpose, right? Now here this is written like a column right now. If I do the transpose of this one, it will be written like a row, right? Written like a row. But just keep this in mind, this is also n cross n and that will also be n cross n. It's just a matter of representation. Okay, if something is a column matrix, right, 1 0 1, and if I take the transpose of that one, so 1 cross 3, so rows, the columns become rows and rows becomes columns, so it becomes 1 0 1. So it looks like from a column matrix it became a row matrix. That's a representation. So from a column matrix it will become a row matrix, and this transpose, right, will go inside also because the inside elements are also matrices, right? So each element will be transposed, right? So it will be C transpose, then CA transposed, okay, then CA square transpose, and go on until C n minus 1 whole transpose, right? So now I have taught you this property, right? So CA transpose, what will this be? This will be A C transpose, right? A C like sorry, no, E transpose C transpose basically. So this will come out to be, this is basically my observability matrix. Okay, I will write this in a more formal manner. I'm just explaining it to you. This is C transpose, this is A transpose, this is C transpose, this is A square transpose, this is C transpose, and it is keep on going on like this, right? And this is n cross n, don't forget, this is also n cross n. This is not a row matrix, right? This is n cross n. Okay, now right, each matrices here inside were like a single row, right? Now each matrices here is like a single column, just like this column changed to row, and row can be changed to column with transpose. So just it's a matter of like just like a few mathematical equations, not that. Okay, changes. So the proof, right, the transpose of A square, like rank of A will be equal to rank of A transpose, equals to rank of A transpose if A is a square matrix. Square matrix is number of rows and number of columns should be same. So A is square matrix, right? Now if A is square matrix, so I will just take a few examples and from there we will understand it. So let's say I have this 0 0 1 3. Now what if I take a transpose of this? First, what is the rank of this one? How many number of independent rows minimum, like independent rows or independent columns are there? Whichever is minimum, I will take that as a rank. So I see this is 0 0, okay, and this is 1 3. So there is only one independent row, right? Why? Because if I multiply this whole equation with 0, I will get this back, right? So only this is the independent row. So but how many independent columns we have? We have again 1, right? If I multiply this one with 3, I will get back this column. So again my number of independent columns is also 1, so rank is 1. Now if I take a transpose of this one, okay, this is my A, now this is my A transpose, this is 0 1 and this is 0 3. Okay, so what will be my rank of this one? The rank of this one, right? Rank of A transpose again will be 1. Why? Again, right, if I multiply 3 with this one, I get this one, okay, the row, right, basically. So the row is dependent, so again I have only one independent row, so my rank is 1. Okay, again I will take another example. Let's say this is the first example. Second example, let's say this is 2102, okay, 2102, and what is the rank of this one? You say, what is the rank of this one? Rank of this one is 2, right? Because these and these are not dependent on each other. Or you can find the determinant and check it's not 0, so hence it will be a full rank matrix, right? So it is 2. Again if I take the A transpose, this becomes 2 0 1 2. Again you see that the columns are independent and the rows are also independent, so my rank, right, rank of A transpose will be equal to 2 itself. Okay, so yeah, this is basically what my rank defines. So now, right, we'll basically do the Kalman's test, but I think we have to end this lecture because this lecture has already been extended. So in the next lecture we'll do the Kalman's test, the Gilbert's test, and like few questions. Okay, so yeah, I thought I have to do only one lecture for observability, but it got extended due to the proofs and all. So in this lecture what we learned, what is the basic meaning of observability. Okay, and to start, let me go. So what is the basic meaning of observability? From like, why did observability came? Due to controllability itself. We have to make the system controllable. Even if I am not able to control all the state variables with my input, what I will do, I will observe the state variables and then feed it back to the input, and from there I will be able to control my state variables, right? And I will get my desired state basically. Okay, or make the system stabilize. So that is important. So I capture the data and then give it back to the feedback, right? So yeah, controllability means it needs to observe states, okay, and observability means it needs to observe states, and controllability means it needs to control the states, basically stabilize. Okay, so yeah, that is what we learned, few key points. Then I told you the state diagram and how you actually practically do it, right? With the help of an observer, I like drawn it in diagram, and from there we understood many things. Like I proved to you how does the error function is in terms of the eigenvalue, okay, and eigenvalue has to be negative for my error function to go to 0. It has to decay, right? It has to be a decaying function. Okay, so yeah, then we understood the Kalman's test of observability. I tried to start the proof, okay, and we got to the end of the proof, right? For the system to controllability, okay, basically this condition should follow, right? My this matrix should be full rank, okay, rank of this should be n for my system to be controllable. For okay, in the next lecture I will further explain the Kalman's test, and we'll do the Gilbert's test also. That is basically for diagonal matrices, and also for non-repeated eigenvalues and for repeated eigenvalues, and then we'll solve a few questions. Okay, yeah, thank you for watching.